Okay, let's get started. I am recording here. So 9.4 subspaces and bases. All right. Okay. Let me write down the definition first. Subspaces. Okay, so let V be a vector space and W be subset of V is said to be a subspace. When do we call the subspace of V? If AX plus BY with the vectors. So basically on the close addition and scalar multiplication at one time, right? Looks like in vector space, which is W is a subset of vector space V, right? And AB is a real number, and X and Y is in vector in W, all right? Okay, now, we have theorem. Subspace or vector space. Subspace or vector space. Let W be a non-empty collection of vectors in a vector space V, then W is a subspace if only if W satisfies the vector space axioms. Using the same operation means addition and scalar multiplication, right? Using the same operation. This was defined on V. So means addition and scalar multiplication. Okay, so I brought here vector axioms from here. So this is a vector axiom. 10 vector axioms, right? Make a shrink a little bit. Okay. So subspace or vector space. Let me write down two theorem, and then let us do example. We say the corollary span is a subspace. Let V be a vector space with W is a subset of V if W equal to span of vector V1, V2, V sub n, then W is subspace of V. So we have an example for this one. Let us do that later. And then one more. Theorem. Spanning set. So let W is a subset of V for a vector space V, and suppose W equal to span V1, V2 until V sub n. Let U is a subset of V, be subspace for such that V1, V sub 2 until V sub n is in U. Too sloppy. Let me send this one. Where I am, U, then it follows that W subspace, no, subset of U. Okay, this means any subspace that contains a set of vectors must also contain span of these vectors. Okay, now we have a subspace test. Procedure. Subspace test. Okay, suppose we have W is subset of a V. So must the following three conditions hold. If W is a subspace of a V, we must follow three conditions. Number one, which is using the operation of V, right? So vector space V, so we are following same operation with a vector V. That is close under addition and scalar multiplication, right? Two operation. And then we have another condition, which is zero, additive identity. We have in the vector axioms, right? So number one, the additive identity, zero vector over V is contained in W. So we can say that 0 is in W, right? Number 2, vector V, sorry, V W1, W1, one in W, and vector W sub 2 is in W, then close on the addition, plus also in W, right? Number 3, V1 is in W and scalar. See? So product CW is on also W, right? Okay, so missing, huh? That is a close on the addition from the vector space, right? And this one closed under scalar multiplication, right? From the vector space. Okay, let's do this one. The VB RB purely vector space. Then B is a subspace of itself. Similarly, the set zero vector containing only the zero vector. Is also a subspace. Subspace. Okay, so look, the vector space V has a, since a vector space, right? They require, I mean, they satisfied all the 10 axioms, right? So since V is vector space, V satisfies the 10 vector space axioms. Oops. Axioms. Thus, it is satisfied. Zero in there also, right? And then close on the addition and close on the scalar multiplication. So it's satisfied. Three conditions. Okay. All right. How about the zero vector? Thank you. Your message. Is subspace. Okay, we have a zero vector. A set. Okay, so 0, the first condition, 0 is in the set of 0 vector. So it's satisfied. The condition. Secondly, so W1 is in the set of 0 vector. Also, W2 is in set of 0 vector, right? What this means? This means the vector W sub 1, which is 0, and vector W sub 2, which is also 0, right? Okay. Then we have close on the addition. We want to show that. So vector V1, I'm sorry, W1 plus W2, then 0 plus 0, which is 0. Okay, more clarify. So 0 vector. Yeah. So to satisfy it, the closed addition. Close on the addition. Close on the addition. Okay, number 3, scalar multiplication. So let's see the scalar. And W1 is in 0 vector. That is W1 equal to 0 vector, right? Okay, so we have a C vector V. I'm sorry, W1 equal to C, W sub 1, which is 0 vector, which is 0, right? Which is 0, right? So it's still satisfied. Under the close close under the scalar multiplication. So we can conclude. Therefore, the set of a 0 vector is a subspace of vector space V, right? Okay. One more thing. Thank you. Direct message. Okay. Let polynomial degree 2 be the vector space of polynomial of degree 2 or less, because they said at most or no more than 2, right? This means degree 2 or less. Or sometimes they're using at most 2 or no more than 2. Okay, All right, now we have let W is a subset of the polynomial degree 2 and most degree 2 be all polynomials. Let me denote polynomial like that. And then have 1 as a root. Okay, have 1 as a root means it's a polynomial, so we can use that p of 1 equal to 0. That means when x equal to 1, we can find the root, right? Yeah, so basically, graphically, the root is on the x-intercept, right? All right, so W, okay, show that W is subspace of polynomial and most degree 2. All right, so we had this one before, right? So polynomial and most degree 2 has the form like this. Set of polynomial p of x equal to ax squared plus bx plus c, right? This is the form of n most degree 2, right? It's okay, a is 0, then we have a linear, right? It's okay because they say that at least, not at least, n most degree 2, right? And then a, b, c are real numbers. And the condition, this is a general condition. Then we make such that more detail, like a specific detail, which is p over 1 equal to 0. Okay, so the first one is general expression, and then such that after such that we give them to detail information. All right, okay, let's make that the first condition, number 1. 0 polynomial, right? So we have 0 polynomial so we have p of x equal to 0x squared plus 0x plus 0, which is 0. So we get p of 1 equal to 0, right? So we are using 0 polynomial is contained in W. Number 2, the clause under close addition, right? Close under close. Yeah. This is sounds okay. Okay, so we have the let p over x in W and q over x is in also W, right? Okay, then we have a p over x plus q over x. Okay, in W, that polynomial, which is P over 1 plus Q over 1, right? So there will be 0 plus 0, which is 0, right? So that P over X plus Q over X, also in W. Number 3, close under scalar multiplication. Okay, so scalar. Let C be scalar. Okay, then we have a P over X is in W, right? So C P over X, then P over X in that W, we can express P over 1. And then C P over 1, which is 0, right? So C P over X is also in W, right? So it's close on the scalar multiplication. So we can say that W is subspace of a polynomial, the n most degree 2. All right? Okay, so let us do one more. There's a lot I have to cover. Okay, I want to skip the null space then. Maybe with the null space next time. Okay, I want to do this one. Given V1, V2 in vector space, V let H is span V1, V2, show H is subspace. Okay. The first one, 0. What is the span? How do we express the span of a vector V1, V2? So we can express as a linear combination, right? Thank you, during message, right? Yes. So we can express 0, which is span. So we have a 0 vector V1 and plus 0 vector V2 because it's a span, right? Yeah, we can express it this way, right? Okay. So then this is, we can express as a written as a linear combination. 0 is in H, right? Since 0 is written as linear combination. Okay. All right. Number 2. We have U. Same thing. U we can express as a linear combination. So there will be C1 vector V1 plus C2 vector V2. Let's say that this is in H. And also vector V, which is D1 vector V1 plus D2, vector V2 is also in H, right? Because we can express as a linear combination of vectors, right? All right. Okay, now close under addition, right? So we have U plus V, which is this. Copy. Plus V, which is that. Okay, so I can arrange C plus DI. Yes, thank you, different message. So we can arrange this on C1 plus D1 number with a vector V1 and C2 plus D2 with a vector V2, right? Okay, we can express this one as this one as a k sub 1, V1 plus, and this one as we can express k sub 2 and V2, right? Okay, look, this one also we can express as a linear combination, right? So this is in H as well. So it's closed under the addition. Number 3. Let's see the scalar. Okay, we have a CU, which is CU was C1 V1 plus C2 V2 is in H. So let's denote, distribute. Hold on 1 second. What I'm doing. Distribute. So C, C1, C sub 1, V1 plus C, C sub 2, V sub 2. Now we can express this one, L. So L sub 1, V1 plus L sub 2, V2, right? Which is linear combination, right? So we can say that this is in H as well. So it's close under scalar multiplication. Therefore, H is subspace of vector space V. Okay, let us see using just null space. All right, so null space, let's see using the null space. Terminology, right? Null space. So null space is the set of all solutions of homogeneous equation. All right, so homogeneous equation. I have this one here. Come on. Yeah, this is homogeneous equation. We did at 1.2, right? All right. Then we can express this one as A as a matrix and X vectors and equal to 0 vector, right? Okay, so AX equal to 0. If we are expressing as a, thank you, Alan. If we are expressing this one, null space as a set, so we denote like that, then X such that very general like X, then we are talking about the detail, right? Specific, what kind of X we need. X is in or n entries and dimension, right? And AX equal to 0. Yeah. All right, so let us do this one. Let's make a subspace. Show that. Null space is subspace. Okay, so we have 0 is in null space because we have AX equal to 0 vector, right? So we have 0 is in the null space of A. Number 2, let's say that let U equal to null space of A, and vector V is also null space of A, right? Okay, look, U is in there, then U is in Rn, and A, U equal to 0, right? Okay, same as V is there, such that V is in Rn, and AV is in same as the 0 vector, right? So that is, so we have AU equal to 0 vector and AV equal to 0 vector, right? That means, okay, now A U plus V, then we distribute, so we have AU plus AV, right? Then AU equal to 0 vector, yes, thank you, Divine says. And AV, which is 0 vector. Which is 0, right? Yeah. So we get AX equal to 0, right? So everything we get 0. So it's closed under the addition. Okay, number 3, scalar. Let's see the scalar. Then we can use A, C, U. Then scalar, we can use like this. All right, then AU, what do you get? We have a 0 vector, right? So there will be C, 0, then, which is 0, right? Okay, we have a D, oops, we have this, we still get 0, like their definition. So it's a close under the scalar multiplication. Okay, so we can conclude null space of A is subspace of Rn. Yeah. Okay. Any question? Thank you very much. Okay. Thank you, dear message. All right, so let us talk about basis. Basis. Oh, before that, maybe we make a note, some note. We have a line, something like that, right? So some note. Note. The vector space are two-dimensional, right? It's not subspace of R3, right? So two-dimension and three-dimension. So must be same dimension, all right? Okay. We have another note. A line in R2 not through the origin. Then it's not subspace of R2. Like that. Because 0, 0 is not in R2, right? Not in, right? So we had this symbol before. Okay, let's talk about the basis. Basis definition. Basis. Okay, let V be a vector space. Then vector V1, V2, until Vn is called, oh, what's going on? A basis for V if the two conditions hold. Okay, number one, span of vector V1, vector Vn, vector space, right? And we have vector v1 and vector vn is linearly independent. So we knew that span is set of all linear combination, right? And linear independent means trivial solution. Okay. Okay, so standard basis, right? Standard basis. We have R3. So we have E1, which is 1, 0, 0, and E2 is sub 2, which is 0, 1, 0, and E sub 3, which is 0, 0, 1, right? So we had a 2 by 2, right? Before. This is a 3 by 3, 3 dimension. Okay. Now we can use more, right? So n dimension, we can express that too, right? Okay, now polynomial again. Since we understood polynomial, let polynomial at most degree 2 be the set polynomial of degree no more than 2 and most 2, same thing. We can write. So P sub 2, this is the vector space, right? And this will be, we can express as a span of x sub 2, x sub 1, 1. Not x sub 1. X squared, not the x sub 1, x and 1. The constant term, right? Okay. So think so P2 we can express as x ax squared plus ex plus c, right? So it's a linear combination. Okay, now they ask us is the x sub 2, I'm sorry, x squared, x 1 basis for P2. Question mark. Okay, so they already give us, right? The polynomial at most degree 2 is a span of x sub 2, x sub 1, not x sub 1, x squared, x1, right? Now we need to show that they are linearly independent. Okay. Since polynomial degree 2 equal to span of x squared x1. Oh, we need to show we need to show that. X squared, x1 is linearly independent. Okay, how do we show? All right, so we had general form, right? Copy. Okay, equal to 0x squared, because we need to show trivial solution, right? So we have 0x squared plus 0x plus 0. Okay, look. They're corresponding, right? So ax squared equal to 0x squared. Bx squared, I'm sorry.
Okay, but first you'll have to unlock your device.
My Google. Scare me. Oh my gosh. Bx equal to 0x, c equal to 0, right? So a equal to 0, b equal to 0, c equal to 0. It's a trivial solution. So therefore, this is a basis for polynomial n most degree 2, since it's a span of vectors and the set is linearly independent. Is okay? All right. So let's talk about the dimension. Definition. Dimension. A vector space V is of a dimension n if it has a basis consisting of m vectors. Okay, so we called finite dimensional. So n is less than infinity. So we call finite dimensional. All right, so example. So we have polynomial degree 2, right? And most degree 2 be the set of all polynomial of degree and most to find the dimension of polynomial and most degree 2. Okay, so the dimension, they say that dimension, we can say n dimension for the basis, right? Okay, earlier we had a basis previously. So P2 has x2, x and 1 basis. So m vectors, which is 3 vectors. So 3 dimension, 3 bases, 3 bases, bases. So P2 has 3 dimension. It's okay. All right, so we talked about the spanning set earlier. Let me write down one more. Okay, let us do this one, and then we're done. Let me just directly using that. Find a basis for 1 0 0 0 4 0 0 0 and 0 1 0 0 2 -1 0 0 and 0 0 1 0. Very good. Yeah, we can conclude that, right? So dimension for the polynomial n plus 1. Good job. N plus 1 dimension. Okay. Look, this one. We're gonna find the basis of the matrix. Okay, so look, this will be, let's make this one will be B1. B1, B2, B3, B4, B5. Yeah. Okay. Then can we say that for B1, which is 4 1 0 0 0, which is 4 0 0 0, which is B2? How about 2B1 minus B3, which is 2 1 0 0 0 minus B3, which is 0 1 0 0, which is, what do you get this one? 2 -1 0 0, yeah, which is B4, B sub 4. Yes, very good. Okay, so we can express this one for B1 equal to B2. And we can express this one as 2B1 minus B3 equal to B4. Okay, so also those are linear combination, right? So we can express which are form of linear combinations, right? So we can discard them, which is V2, B4. Okay, even though we discard B2, B4, we still have the span of set. B1, B3, B5 are still span. B1, B3, B5. Okay, so look, we can say that B1, B3, B5 is basis for can you say the B? So let's take a look. So B1, B3, B5, B sub 1, B sub 3, B sub 5. Can you see that? What can we see? Yes, that's what I want to telling here, right? So can we see that there's a PV column? PV column. This is for is okay? All right, any question about today's lecture? It's very heavy, huh? Okay. Thank you for coming. You have a nice evening. I will see you tomorrow.